Hello everyone, my name is Sulika and I will be discussing with you all the physical chemistry and inorganic chemistry. So these two topics is something which you need to understand as well as apply, and also the one mistake that students generally tend to do is the unit conversion. In inorganic chemistry it is not that frequent, but in physical chemistry the unit conversion plays a major role, even you do questions as well. So, beginning my first lecture in this series, I'll be starting with the gaseous state. As we all know, it is the preliminary idea of any physical chemist would be dealing with, right? So, basically, I know everyone might be knowing, but still, for my convenience, I'll let you know there are three forms that we will be dealing with. One is gases, then liquid, then solid. Why do we study gas phase only? Why not solid or the liquid state? Solid we have a small section, even liquid we will be studying anyway. But whatever studies that are done in physical chemistry are done with the help of gaseous phase. Now, why this gaseous phase is so important? Everyone might have wondered, right? So, coming to this answer, it's because in gaseous phase what happens is we have a large vessel. Say in all the three cases we have, let's make it same size. Okay, considering these all three are of the same sizes, right? Then what happens is in gaseous phase, let's say we have just 5 molecules which are very far apart. So studying simply one molecule would be quite easy, right? So we just consider that in a space there are, okay, let's say a number of molecules, but since they are far apart they have no interaction, neither with the surrounding, neither with the molecules, with nothing. So it's easy for us to study these molecules, right? Now coming to this liquid phase, what happens is molecules are mainly hydrogen bonded. Let's say in case of water molecule, not in every liquids but considering as water molecule. So what happens, water molecules, there are lots of hydrogen bonding, right? Mainly there are two hydrogen bonding, but since it's a full network, so it's a very large number of hydrogen bonding is there in total. So here we cannot study the single molecule, because this is attached to this molecule, this is attached to this molecule indeed is attached to this molecule. So it makes the whole system too complex for us to study, right? So now coming back to this, since it's a solid, so I'll be considering a crystal packing, something like this, right? So now I have told you how complex the liquid system is, right? In case of solids, it's more complex because these are more tightly arranged. Though here what we consider hydrogen bond, which is a weak force, still it's a weak force, we are considering it. But in case of solid, it's a very strong force. It's the lattice energy, which is very high energy. So to study one simple molecule is very difficult, right? Still, we have some assumptions. When we study these liquids or solids, we have certain assumptions and then we proceed towards its study. So, starting with the gas law. Firstly, gas law. Gas law is composed of Boyle's law plus Charles' law. Okay. So what does Boyle's law states? It states that at constant temperature is constant, pressure is inversely proportional to volume. That means as we increase the pressure, volume decreases. Okay. Secondly, we have Charles' law. Charles' law states that at constant pressure, so here pressure is constant. Okay. Here it states that volume is directly proportional to temperature. That means we are not changing the pressure. But as we increase the temperature, volume increases. Simply, if we consider water or anything, let's say consider water because the simplest system that we can study. We have taken water, we boil it, okay, in an open atmosphere, because atmospheric pressure is fixed, right? It doesn't changes abruptly. So atmospheric pressure is fixed at 1 atmosphere. We are boiling water, so what happens is the volume increases because they're increasing the temperature. So this is what Charles' law states. So now, when in gas law, what happens is we simply make an addition of these two things, and what we state is PV, these two terms, by T is constant. Okay, this is simply the gas law that it states, and every law that is based on gas is basically based on this laws. Okay, this is also known as equation of a state and is also represented, or what we can say is total pressure is equals to x1 P plus x2 P2. It's simply the sum of the total pressure, that is it all. Second we have is Graham's law of diffusion. Now since the definition itself states it's related to diffusion, so diffusion is related to density. Okay, it's related to density. So what happens is that in this equation we will be needing three things. One is the rate of diffusion, since we're talking about diffusion, density, and then the molecular weight of anything what we are dealing with, right? So the equation writes as d1 by d2 is equal to d2 by d1 is equals to m2 by m1. Here this is the rate of densities or rate of diffusion, what we can call it. This is the densities and this is the molecular weight. So Graham's law states that the rate of diffusion of a gas is inversely proportional to the square root of the density, or let's say like this. Okay, this is what it states. Basically it is this is what it is stating, and this we have abbreviated and made it this. And similarly it also states that the rate of diffusion of a gas is inversely proportional to the square root of its molecular weight. So with those equations we'll have to remember certain other equations, and simply an elongation of equation of a state. I'll be doing equation of a state. What we derived is PV is equals to nRT, right? This was our equation of a state. So now we also know that kinetic energy is equal to 3 by 2 PV. This is equal to, so now from this equation what we know is PV is equals to nRT. So kinetic energy is equals to 3 by 2 nRT, right? So now what we initially we had an equation relating energy with the pressure and volume, but not with the temperature. But now with the help of this equation of a state we have correlated energy with respect to temperature. So this will also be helpful in solving numericals. So now we come up to the next important equation of the gaseous state. What is Maxwell distribution? Maxwell distribution of velocities. So I'll just be writing the equation once, I'll not be deriving it fully. You'll get it in any standard books, the derivation. So the equation states dnc by n is equals to 4 pi into 2 pi RT root over 3 by 2 e to the power of minus mc square by 2 RT into c square dc, right? So this is the equation, and based on this equation we have three velocities. V most probable velocity, V average velocity, and V root mean square velocity. I have represented as MP as most probable, AV as average, and RMS as root mean square velocity. So this is equal to root under 2 RT by M. This is equal to 8 RT by pi M, and this is equal to root over 3 RT by M. So these three are the equation. Now what we can see is this RT by M factor is common in all the three cases, right? Now one question, and it has come up in the competitive exam as which velocity is high. It has come for 1 or 2 marker question, but let's say now from this what we can see is root 3 is definitely greater than root 2, right? That means V RMS is greater than V most probable. This we don't have a doubt. Now we know that the value of pi is 3.14. So when we divide, this value comes up around 2.54. Okay, root under. Now we have comparison of root 2, root 3 and root 2.5. So obviously what we can see from this equation is V RMS is greater than V average is greater than V most probable. So we should remember this one, because this is really important to remember, and it has come up in the examination. So one should remember this. Also this equation can be correlated and found out, like in certain cases it has come up like one velocity would be given to you. Let's say VRMS is given to you, let's say a value of x, and you are set to find V average. So obviously you can correlate these two equations and then find the value of each other, right? Okay, so with this there is one more thing one should remember. It usually doesn't come up, but sometimes if you're lucky enough these questions come up, like collision diameter and collision number, right? These two questions usually come up. Collision diameter is represented by sigma, and from this we can find this collision number equation as Z1. This is number which is the number of the collisions that is suffered by a single molecule in a certain time. Okay, so this is given by root 2 sigma square V average into rho. This sigma is again collision diameter, this is average velocity, and this is number density. Okay, number density, these things will be given to you. You just need to find this collision number, or sometimes what happens is you need to find this diameter and all these other values will be given to you.